As a second example, we consider problem 336, where we're asked to determine the largest weight W that may be supported by the assembly below if the failure strengths of the cables and bars making up the assembly are given by the table shown. Take a minute now to pause this video and try the problem yourself. Resume playing when you're ready to see a solution. In limit load problems like these, we have to be careful not to assume that any one particular segment will fail first. Even though we're looking for W, we will treat that as a known and find the loads carried by each of these members as a multiple of W. Then, evaluating the limit load for each individual piece of the assembly, we'll be able to identify the limit load by choosing the minimum weight of a set that results in limit loads for each of the individual members. Among these 5 elements, the one that's easiest to treat is the tension in member CD. If we choose to isolate the weight itself, then vertical equilibrium will give us that the tension in CD is equal to the weight. Where else should we focus our attention? Important places for us will be the joint at B, where we have several members coming together, and the joint at C, where several members are coming together. We should be able to write 2 equilibrium equations for each one of these joints, and that will give us 4 additional constraints that will enable us to solve for the load carried by each member as a multiple of W. We might also note here that bars BE and CE are pin connected at their ends, and there are no intermediate forces between those pins. And again, that will mean that these are 2 force members, meaning that the loads they carry are aligned with their geometry. For each of these cases, we'll use a standard XY coordinate system, and we'll take advantage of the geometry that's shown here to essentially identify what the sines and cosines of different angles will be without actually having to solve for those angles explicitly. So we'll see, for instance, that member EB experiences a rise of 80 centimeters for a run of 60 centimeters, and that means the geometry of this member corresponds to a 3, 4, 5 triangle. Similarly, BC also experiences a drop over run of the same proportions, so this is also a 3, 4, 5 triangle. And the cable segment AB experiences a drop of 45 centimeters for a run of 60 centimeters, and that also makes this a 3, 4, 5 triangle. This will enable us to identify the components of the unit vectors acting in these different directions. We can see, for instance, that the unit vector that points from E to B will be 3/5 in I plus 4/5 in J. The unit vector from A to B, which will be the negative of the unit vector from B to A, will be equal to 4/5 in I minus 3/5 in J. And the unit vector from B to C will be equal to minus the unit vector from C to B, and will be equal to 3/5 I minus 4/5 J. We now look at free body diagrams for joints B and C. At joint B, we're cutting through the cables AB and BC, and as cables, those have to be in tension. We're also cutting through bar BE, and again, as a 2-force member, the force that it carries is aligned with its geometry. It may be difficult to see here, but this is going to be in compression. I'm going to represent it that way. At C, we're also cutting through 2 cables that are in tension. CD has a tension that's equal to the weight. The tension in the cable at C can be represented as the unknown magnitude TBC on a unit vector that points from C to B. So it's equal and opposite to what we have in the free body diagram for B. And once again, bar EC is going to be in compression, so I'll represent it that way. And it's pointing along the x-axis, so it's in the I direction. So in these two free body diagrams, I have a total of 4 unknowns. I have the compression in EB, the compression in EC, the tension in AB, and the tension in BC, and we're seeking to find each of these as a multiple of the weight W. It's easiest for me to employ equilibrium by starting with joint C, because there I have just 2 unknowns, the compression in EC and the tension in BC, whereas joint B, for the moment, has 3 unknowns. Note that once we find the magnitude of the tension in BC from examining joint C, we'll be able to carry that information over to joint B. But for now, it would be better for us to focus on joint C. In the x direction, at joint C, we have the compression in EC minus 3/5 TBC equals 0. And in the y direction, we have 4/5 TBC minus the weight equals 0. And that gives us that the tension in BC is 5/4 of the weight, and the compression in EC is 3/5 of that value, which is 3/4 of the weight. The fact that I got positive expressions for both of these numbers indicates that I have represented the signs correctly. So in fact, EC is in compression and can be represented as this multiple of 3/4 on the weight. I can now carry the result of the tension in BC into the joint at B. And in the x direction, I have minus 4/5 TAB plus 3/5 TBC plus 3/5 CEB equals 0. And in the y direction, I have 3/5 TAB minus 4/5 TBC plus 4/5 CEB equals 0. Now I can take the result for TBC and substitute that in and get 2 equations in the 2 unknowns, TAB and CEB. The x component equation becomes minus 4/5 TAB plus 3/5 compression in EB is equal to minus 3/5 TBC, which is minus 3/4 W. We'll call that equation 1. The second equation becomes 3/5 TAB plus 4/5 CEB equals 4/5 TBC, which is just W. We'll call that equation 2. Again, there are many ways to solve these kinds of problems, but what I'm going to choose to do is to take my first equation, multiply it by 3/4, and add that to the second equation, which will result in the TAB term going away and will give me 9/20 plus 4/5 CEB equals W times the quantity 1 minus 3/4 of 3/4, or 1 minus 9/16, which gives me 7/16 times W. This fraction is 9/20 plus 16/20, which is 25/20, which is also 5/4 CEB. And that enables me to write CEB as 4/5 times 7/16 W, or 7/20 W. Now we might just note here that's a relatively small multiplier, and if we come back up to the figure, we might note in looking at this free body diagram that these tensions TAB and TBC are relatively closely aligned. That is, if they were the same angle, bar EB wouldn't need to carry any compression whatsoever. The fact that there's almost 180 degrees between them means that we only need a very modest force in the bar EB in order to keep that in equilibrium. So it isn't surprising that we have such a modest multiplier on CEB for this problem. We can now take this result and plug it back into equation 2, and we get 3/5 TAB plus 4/5 of 7/20, that will give me 7/25 W equals W. And that gives me that TAB is equal to 5/3 times 18/25 W, which is 6/5 W. So I've now obtained the tensions and compressions in all of these elements as multiples of W, and I can systematically look at each element and figure out what the limit load would be for each of those elements, and then choose the limit load for my system as the minimum of that set. So for AB, we have that 6/5 of the first limit load, W1, is equal to 3.5 kilonewtons, and that gives us a first limit load that's equal to 2.917 kilonewtons. For BC, we have 5/4 W2 is equal to 3 kilonewtons, and that gives us a second limit load of 2.4 kilonewtons. For CD, we have that the tension carried by CD is just the weight, so W3 is equal to 2.5 kilonewtons. That's our limit load for that segment. For BE, we'll choose the appropriate value for compression. Since we have positive values for the two compressions that we solved for, they are in fact in compression, and we'll use that limit load. So we have 7/20 W4 is equal to 1.8 kilonewtons, and that gives us a fourth limit load that's equal to 5.143 kilonewtons. That turns out to be the largest of the set. For CE, we have 3/4 W5 is equal to 2.8 kilonewtons, and that gives us a final limit load of 3.733 kilonewtons. The fact that we got all these different limit loads tells us why we approached the problem the way we did, by taking the weight as a known and then solving for the limit loads for each of these separately, because what these results tell us is that each of these elements reaches its limit load at a different weight. And the maximum value that we can tolerate is the one that corresponds to the most vulnerable element, the one with the smallest limit load, and that will be W2, which will be equal to 2.4 kilonewtons.